Welcome back to your physics buddy. In our last two sessions, we mastered the math and visualization of magnetic forces. But today we are scaling up. In lecture 3, we are exploring the biggest magnet you will ever encounter, the Earth itself. We'll break down the physics of geomagnetism before diving into the piece of technology that changed human history, the transformer. We are going to explore how we use magnetic induction or set up and step down voltage to move energy across entire countries. This lecture is where the electro meets the magnetism. If you haven't seen our deep dives into the Wilson and Buffo framework in lecture 2, I highly suggest catching up so you understand the force and flux principles we're using today. This is the final piece of our magnetism foundation in unit 12. So in the last class we talked about various configurations of current carrying wire which can show its effect of magnetic field around it. So in today's class we'll talk about some more of those examples, we can say configurations. Apart from that, we'll see some practical application as well as electromagnetism, that how that magnetic field which is created can produce current. So here there is another configuration. We already discussed it. In order to calculate a magnetic field on the axis of a loop at a certain distance. So at this point P, if you want to calculate magnetic field due to this current carrying loop, that magnetic field comes out to be this. It is again an important relation. We do talk about the derivation aspect, but I don't think so there it is necessary. You can simply remember the relation and get the magnetic field. Now let us try to understand what are each component, or you can say each physical quantity representing here. So there is mu naught, which is permeability, and the mu naught has value of 4 pi times 10 to the power minus 7. So that is something you need to remember. N is the number of turns of the loop, I is the current passing through it, R is the radius, where x is the distance of the point from the center of the loop. This is the radius. So these are the things which must be given in order to calculate the magnetic field. So generally in all the cases it is given. Then we can talk about magnetic field in the current carrying solenoid. It is nothing but mu naught Ni. I would rather prefer to remember it with this relation mu naught Ni, where this N is number of turns per unit length. So sometimes the small n is given in the question in this form, in which it says that 20 meters of length of solenoid contains 300 turns. So you can calculate this n directly by length, or you can say number of turns per unit length. You can just write it down. And here also it shows that same relation. But sometimes question has the value of small l. So we have to not, you can say, consider length. This is called linear turn density, the small n which I was talking about. Then there's a small question, I can say an easy question. Let us just try to calculate whatever is asked in the question. So question says that there is a solenoid. So again remember, solenoid is a configuration in which these kind of number of turns, or you can say coil, we observe like a spring, you can say. So it is 0.3 meters long with 300 turns. So here number of turns, that capital N is given as 300, or L is given as 0.3 meters. Current is given as 15 amperes. What is the magnitude of magnetic field near the center of the solenoid? So what we will do, we will use this formula. We'll substitute the values of each, and we'll have the value of magnetic field, which comes out to be 18.8 millitesla. Millitesla means 10 to the power minus 3 Tesla. The second part says compare the result with a field near the single wire in example 19.6. For this we have to go to example 19.6. I guess if we know the application part of this particular equation, we are good to go. So let's move ahead. Now we will talk about what if two wires are placed parallel to each other and they both carries current. how will the two wires behave? What application of this particular configuration we do observe? So when we do this, when we just try to observe that what happens, so we just find that these two wires carrying current will produce magnetic field in one particular direction. And because of this magnetic field, there must be some force which is acting on the wire. And what you have to remember here is if the wire is carrying current in the same direction, the force which is acting, it is going to be attractive. That's all. This is what you have to understand. And if the wires are carrying current in such a way that they are opposite in direction, the force is going to be repulsive. It will completely depend upon the direction of current. Always remember. So this is the reason why if you generally observe the wire of any electrical device around yourself, so you'll find that wire are joined in this crisscross pattern. This is the reason because these two wires must carry current in the opposite direction, and if they are not, you can say, put in this way, they will repel each other, and if they will repel each other, they will be far apart. And this can be, you can say, avoided by just putting them in the crisscross form, which will just try to neglect that force. I hope this makes sense. Did you understand this thing? Arnav, are you there?
Yes, sir. I was on mute.
Does this make sense?
Yes, sir.
What did I told you? Tell me.
You explained about the repulsive and attractive force in the diagram. See,
Like how they act. What is the condition of force being attractive and what is the condition of force being repulsive?
if these two arrows are like connecting, it's attractive.
I'm asking what is the condition in which case the arrows will be like that.
It depends on the magnetic field, the direction of it.
Not exactly that. Pay attention. Although this thing shows that if you focus, you will be able to do more out of it. I'm just talking about the direction of current. If the current is in same direction, the force is going to be attractive. If the current is in opposite direction in both the wires, the force is going to be repulsive. That's all. That is what we have to keep in our mind. That is the application part of these forces, or you can say current carrying wires or materials. Now let us just talk about magnetic materials. So in order to understand magnetic materials, we have to understand this one term called electron spin. So we have to understand this thing. The source of magnetism is basically the magnetic materials. What makes materials magnetic and what makes different forms of material, it will depend upon their electron spin. So what this electron spin is? The modern atomic quantum theory tells us that the permanent type of magnetism, like that exhibited by iron bar magnet and is produced by electron spin. Classical physics likens a spinning electron in Earth rotating on its axis. However, this mechanical analog is not actually the case. Electron spin is a quantum mechanical effect with no direct classical analog. Nonetheless, the picture of spinning electrons creating magnetic fields is useful for qualitative thinking and reasoning. In effect, each spinning electron produces a field similar to the current loop. This pattern resembling that from the small bar magnet enable us to treat electrons magnetically speaking as tiny compass needles. So we just have to understand this thing that if there is a metal and that metal contains of spins, and these are electron spins basically. So these electron spins can be aligned like that, can be aligned like that also. So if these spins are arranged in a specific manner like that, The material is supposed to be magnetic. If it is supposed to be available like that, the material is known as, I would say, paramagnetic or ferromagnetic. Whereas like that, I will call diamagnetic. So this is how we distinguish the materials. Every metal or element has some property of magnetism, but those properties can only be useful if you don't have to apply more of electric field around itself so that it will be aligned in the manner diamagnetic materials are. So that is something we have to understand here. In electron, or you can say in multi-electron atoms, the electron usually are arranged in pairs with their spin oppositely aligned. That is one with spin up and one with spin down. So that is something is explained in terms of chemistry most of the case, because in chemistry also we learn the same thing, magnetic material on the basis of their spin alignment. If something has unpaired electron, so they'll be considered as paramagnetic, and something which has, or you can say some compound which are fully filled, like paired electrons only, then in that case we observe that those were supposed to be called diamagnetic or do have some magnetic properties aligned in one direction. In this case, the magnetic field will effectively cancel and material cannot be magnetic. Aluminium is such a material. So generally in those material which is like that, we do observe this thing. Then we do talk about ferromagnetic material. So this is how you can compare them. So this is how we can also compare the magnetic materials. If they are lines, if the domains are aligned in one direction, they will be considered as paramagnetic or ferromagnetic. If they are aligned in the same direction like that in the C part, or you can say in the bar magnet case, that is something called diamagnetic material. Although every material can be made diamagnetic at some point of time by putting it into a external field. So external magnetic field can do that, aligning the magnetic or movement in the one direction. So this is something which we can also understand from this particular part, that if this is a case that we haven't closed the switch, so whatever battery is there, it will produce nothing. It won't be able to produce current. So that thing is something which is not capable of attracting these electron fillings. Once you close the circuit, the current will flow, it will create a magnetic field, and that magnetic field will pull up the iron fillings. What does it indicate? Indicate that iron fillings will be getting some force in the upward direction. South pole will be attracted to us, north pole will be repulsive. So that is the reason we saw them that they are attached in the form of spikes to the surface. And that's all because of this south and north pole development of the iron fillings. So that is another example how we can distinguish the material on the basis of this. So whatever the case, the field which is about to be there because of solenoid, it is calculated by mu naught Ni over L. So these were the relations that we have to keep in our mind. Let us just talk about this particular question. Example 19.1. So here the question says, I guess you should try this out. Let me just try to make you understand what is given. And you can try this question out. So number of turns given is 200 and length is given as 30 centimeters. So we can write it as 0.3 meters. Is limited to carrying a maximum current of 2 amperes. So current is also given as 2 ampere. The scientist in the lab needs an interior magnetic field strength of at least 2 Tesla. So field is also given as 2 Tesla, and are debating whether they are able to employ a ferromagnetic core. So is the field possible if no material fills its core? So we have to just understand or find that is this field possible. So what you have to do is you have to solve the magnetic field using this particular relation which we saw, mu naught Ni over L, and find whether this system or this coil will be able to generate this field or not. If it is able to do so, then the ferromagnetic core will be magnetized. If it is not, if it will not be. So just solve this and tell me what it is going to be, like how we can find out magnetic field and what it's coming out to be. Solve it. It's easy. Are you trying?
Yes, sir. I'm getting error. Not sure.
You just have to substitute the value. So mu naught is going to be 4 pi times 10 to the power minus 7.
That's what
N
I
is
did.
going to
Yeah.
be 200. Current is 2. Length is 0.3. We just put it here. Three zeros. Mm-mm. We just have to solve this. So when we solve this, 4 pi times 4,000 divided by zero point 0.3. So it is coming out to be 0.16 10 to the power 5 into 10 to the power minus 7. So it is going to be 0.16 into 10 to the power minus 2. So we can write it as 1.675 into 10 to the power minus 3, which is obviously less than 2 Tesla, because we need the field strength in this question. According to this question, sorry, we at least need 2 Tesla. But as per this question, we are getting only 0.16 times 10 to the power minus 2, which is way more less than that. So you can see here, without any core material, the interior magnetic field clearly would not be large enough, because it is going to be less than that. So they have considered it as 1.7, but we can do that as well. 1.675 is the precise calculation. So the required field is about 2 Tesla, and we are getting 1.7 times 10 to the minus 5 Tesla, or about 1200 times as strong as the answer of to part 1. So we need at least 1200 times more than this particular field we are creating right now. So we must be putting some material into the core. Now, how can this thing be done for this particular question? So we'll simply put a material, that material which is like huge magnetic in nature, and when it is kept in its core, that material will pull the magnetic field strength to the next level. And some materials can do that as well. And that is something we call, uh, you can say, diamagnetic materials. Does this make sense? Because this is important, the application part, like how and why we are doing this. That is the most important, or you can say, better example to explain all of these characters. So we also have electromagnets, and electromagnets are those kind of materials which, when they get current passing through them, their magnetic strength appears. And when there is no current, they are just like other metal placed on the ground without having any field strength or anything. Now, we finally came across Earth's magnetic field. What is Earth's magnetic field and what is the main function of this? Let us try to understand first this one.
An aurora looks like a beautiful display of lights in the sky. These are some auroras that were spotted in the sky over central Alaska. We can also see auroras from space. This is what an aurora looks like from the International Space Station. The name of an aurora changes depending on its location. If you're in the northern hemisphere, it is called aurora borealis, or northern lights. And if you're in the southern hemisphere, then it is called aurora australis, or southern lights. So, what causes these beautiful displays of lights anyway? The sun. That's right. Even though auroras are best seen at night, these colorful displays are caused by our ever-changing sun. Reaction makes green and red light.
So this is the most important, we can say, application of Earth's magnetic field. If Earth's magnetic field was not there, then then life is not possible on Earth. You can say that. Every aspect of this part of, we can say, the solar system, that is Earth, has, you can say, all the possible measures, or you can say conditions which can support life. So that is why we are living here. The most important aspect of Earth's magnetic field. And again, you can see this image to understand that how field lines actually originate. So as per our understanding, this is called geographical north, and this is supposed to be called geographical south. But if we talk about magnetic north and magnetic south, they are different. Magnetic north is this way, and magnetic south is supposed to be here. What we have to understand here is that the angle between magnetic south and magnetic north, or you can say magnetic south, it is about 11.4 degrees. This is huge because this is the reason why one part of the pole receives maximum sunlight, whereas in another 6 months, the another pole receives the maximum sunlight. Like there, for 6 months, sun never sets on one pole, and for the 6 months, sun never set for the other pole. And that is only because of this alignment, this shifting of magnetic north and you can say geographical north. So that is one thing that we can remember about this particular part of this chapter. Magnetism is everywhere, wherever we find there is some magnetic field which is creating, or you can say helping Earth to exist, or you can say flourish life. Then there are few terms. We'll discuss them through the numerical part directly. If we move ahead, these are the few diagrams which are explaining that how magnetic confinement can be shown. A charged particle entering into a magnetic field at an angle 90 degree will automatically move into the helical path. This helical path is because of the nature of charge and the direction of magnetic field. Whereas in a non-uniform bulging magnetic field, the particles spiral back and forth as though confined in a magnetic bottle, just like that. So very unique, or you can say observation pattern. Similarly, if a charged particle is trapped in Earth's magnetic field, the region where they are concentrated are called Van Allen belts. So here we can see the protons are accumulated, and here there are the electrons must be aligned because of the Earth's magnetic field. So some important diagrams which are needed to define the behavior of, or you can say position of charged particle. Let us just talk about this particular problem. The problem says a tightly wrapped cylindrical solenoid has 5 centimeters diameter. So this question is going to be interesting. So this is kind of solenoid we have. It is a cylindrical one. It has a radius of 5 centimeters, or you can say diameter of 5 centimeters. So you can write D is 5 centimeters here. And 25 centimeter length, whereas the length is 25 centimeters. It forms and consists of 1,000 circular wire winding. It means it is given that there is 2,000 turns. 2,000, 1,000 turn is there for this much particular length only. So huge number, first of all. Wire winding with a total resistance of 2 ohms. These wire has a resistance of 2 ohm. It forms a complete circuit with 12-volt battery. Potential is also given as 12 volt. Question says near the center of the solenoid there is a small circular current carrying coil. Okay. So at the center, or you can say the axis passing through the center, 0.6 centimeter radius circular current carrying coil is present. So it will be like that. It would be like that. And its radius is 0.6 centimeter. As a current of 1.25 amperes, there is a current going on inside 2.5 amperes and 25 concentric loops. 1.25 amperes and number of turns is given as 25 concentric loops. So this is a complex example, a coil within coil. The coil is oriented such that the solenoid magnetic field is parallel to its area. So whatever, basically they are coil within coil in a perfect direction, or you can say. What is the magnetic field strength near the center of the solenoid? How much current does the solenoid have? How much torque is exerted on the small coil by the solenoid field? So we have to find out current. We have to find out magnetic field at the center, as well as we have to find out torque. So whatever we have given here is, it is written. So I guess you should try it out once. Just try to understand. I guess you should draw the diagram once again. Make sure you draw two coils, coil within coil. One is represented here as current in solenoid is IS, whereas current in coil is given as IC. So similarly, potential across the setup, or you can say potential across the solenoid is itna. Number of turns is 1,000. Resistance is given. So how can we find out the current? Think about it.
6 amperes.
Let's see. So the one thing that we have to understand here is the outer coil must have some radius, which is we already know. Whereas the inner coil. So whatever magnetic field this inner coil is generating, apart from this, whatever current is flowing in this outer coil, everything must be aligned, or you can say the net result will be calculated at this length. So for the outer, you can say the bigger coil, or you can say the solenoid, the current can be calculated using Ohm's law, which is V is equals to IR. So I is going to be V over R. Potential which is connected is 12 volts, resistance is 2, so we got 6 amperes of current. Similarly, we have to find out the magnetic field at the center. So we can simply use magnetic field relation for solenoid, which is going to be mu naught capital N I over L. If we apply this, we'll get the magnetic field magnitude, which is coming out to be 3.2 times 10 to the power minus 2 Tesla. Now, as there is another coil inside, and this coil must be, you can say, generating some torque. So you have to understand first this particular formula. The torque is nothing but M cross B. I told you that there is an electrostatic analogy. Whatever formulas we saw in electrostatics, similar formulas we are looking here as well in magnetism. Whereas P, which is electric dipole, is replaced by magnetic dipole here. This magnetic dipole is also equals to NIA. So for this, we have to find out number of turns of coil. We have to find out current in the coil. We have to find out area, which is going to be given by pi r square. The number of turns in the coil is 25. Then current in the coil is 1.25 amperes, and area is pi r square. So pi times 6 into 10 to the power minus 3 meters square. So it was 0.6 centimeter. That can be written as 0.000, or you can say 0.006 meters. So it is going to be 6 into 10 to the power minus 3 meters. So conversion is something which is important, and we have to solve every question in SI units by considering meter and everything. So that is one thing you have to keep in mind. Once you got the value of M, we simply multiply it with the value of B and it will get torque like this. So if we solve this, we will get the value of torque. So I would say that you should solve the complete question. You got the complete idea. Just look at the given data now and try to find out the magnetic field and torque and compare the answer.
Yes, sir. I'm
What is,
getting 0.030144 for magnetic field.
and what about torque?
1.06 time tends to negative 4 for torque.
So let us revise all those concepts once again. So we started with understanding electric force. We started with understanding the behavior of charged particle in static situation. So there will be a pole force, or you can say law of poles will act here. Opposite magnets attract, opposite poles attract, and same pole repels. We understand what is the value of 1 Tesla. We understand that how 1 Tesla is defined, and what is the force of magnetic field, force due to magnetic field for a moving charged particle, which is QBV sine theta. Then we understand what is the force, magnetic force due to current carrying wire, which is IBL sine theta or ILV sine theta. Then we talked about right hand force rule to understand or determine the direction of force. Then we talked about the torque acting on a current carrying coil placed in a uniform magnetic field, which is NIAB sine theta. So these were the relations. Like you can just remember these relations to understand, which we have to actually apply. Then we talked about magnetic field due to a long straight wire, which is mu naught I over 2 pi r or 2 pi d. Apart from this, we got the magnetic field due to a current carrying wire. So the magnetic field which is there, it is going to be mu naught Ni by 2r. Similarly, on the axis of loop at this point, we also understand that magnetic field is going to be this. So these were the common relations that we'll be using. And this was the last one which we just solved, which is mu naught Ni over L, magnetic field inside a solenoid, or you can say center of the solenoid. This is the magnetic field. Now let us just talk about few problems here which are required to be solved. Some easy questions you'll be finding here till question number 20, I believe. Let us just talk about conceptual questions are also something. I would suggest that you should read these conceptual questions, try to answer them, and if you didn't find the conclusion, a specific conclusion for any question, just let me know. Let us just solve some numericals here. So just try to understand the first question and tell me what it is asking and how the magnetic force on different ends can be defined. Try this question out. Read this question thoroughly. See what is exactly happening and tell me what should be the answer.
The first one would be oriented horizontally above both of them. Both. The
Like
first
what?
one.
Let me just see this once. So the question is a permanent magnet is vertically oriented so that its north pole is below its south. So north is like that, south is like that. The north end of the magnet feels an upward magnetic force of 1.5 millinewtons. So there is some force acting upward, 1.5 millinewtons. From identical vertically oriented bar magnet. So if there is a vertically oriented bar magnet, identical, so it must be aligned in this way. Then only opposites will, we can say, will not be able to attract, like will repel, and this will feel a force in the upward direction. That has one end located 2.5 directly below the north. So one end must be north. Mega sketch showing the orientation of the second magnetic poles. It is going to be like that. The third identical magnet is brought in the orientation. So I guess you said this as well. That is correct. In the second part, it is saying that there is a third identical magnet is brought in and in oriented horizontally so that its north end is closest to 1 and 2.5 centimeter directly to the right of the north pole. What is the magnetic force on the north end of the magnet? Hashtag 1 now. So this is a permanent bar magnet. This is the one. This is the second bar magnet. So question says the third one must be oriented in this way that it is oriented horizontally so that its north, third one's north is closest to the first. So it must be like that. If I assume north must be like that. 2.5 centimeter directly to the right of north pole. 2.5 centimeter directly to the right of north pole. So the distance between them should be 2.5 centimeter. What is the magnetic force on the north end of the magnet one now? So what is the force on this end now? Now let me just give you a one clear picture of this particular diagram of the figure. One was already placed this way, another was placed this way, the third one was placed this way. So this was north, this was north. Now again one more north is there. So you have to find out the net force direction on this hashtag first bar magnet. Think about it and tell me. What is the direction of net force acting on the first bar magnet?
Wouldn't that be the force of second and first combined.
Yeah, so what should be the direction? It is going to be the net force, but what is the direction? So this north was already repelled by
Northeast,
the first one.
northwest. It should be. Yes.
Yeah, so the net force direction must be like that. So this is one such kind of question where you're supposed to find out the direction of net force. Apart from this, we can try out this question as well. Question number fifth. The question says that there is a charged particle of 0.5 coulombs moves vertically in a field of 0.08 Tesla. So there is a charged particle, it is moved in the direction vertical to the field. So field must be like that. Oriented at 45 degree from the vertical. So field is oriented at 45 degree. So I would say this is the vertical direction. Field will be like that. Now the question is, what speed must the charged particle have such that the force acting on is going to be 10 newtons? So kinda tricky question, because here you have to understand this fact. Once this charged particle enter into the magnetic field, the force will be acting perpendicular to the direction of motion, and because of this, the charged particle will turn like that. So if this turn like that, there must be some magnetic force acting here. Apart from this, there must be some centrifugal force acting outward, which is mv square by r. So magnetic force acting inward, it is going to be qvb sine theta, whereas this force must be equals to mv square over r. So as the question doesn't suggest any radius to the curve, so we can also use that force is equals to qvb sine theta. Force is given to us, we have to find out the velocity, or you can say speed. We can use this formula. So force is 10 newton, it must be equals to 0.05 coulombs of charge. Velocity is something we have to find, speed is something we have to find, magnetic field is given as 0.08. This whole thing must be multiplied by sine 45, which is 1 over root 2. Solve this equation and tell me what is the value of velocity, or you can say speed. What speed this charged particle must possess in order to have this much of magnetic field acting on it. Solve this equation, it's pretty easy now. You just have to substitute solve it. Tell me the value of velocity, what you are getting.
7.07.
7.07. I don't think so. 10 times root 2 divided by 0.05 divided by 0.08. It is going to be 3.535 times 3 meters per second. It's a huge number. I don't know where you are making the mistake, but the question is pretty simple. Velocity must be equals to 10 times root 2 divided by 0.05 times 0.08, because this is what we have here. Charge as 0.05 and field as 0.08. So we have to divide it, and if you solve it, you'll get it around 3.535 times 10 to the power 3 meters per second. It's a huge number. Velocity must be like very much in order to have that much magnetic field with this. So that is something that you can imagine here once again. Now again, question number 6 is very similar to it, 100% similar to it. Solve it and tell me what should be the angle.
I'm getting Arc sine point 2.
Arc 9.2.
Arc sine point 2. So
That
that
is
should
some
be
that is in radians. So let us just see. So charge is given, field is given, speed is also given. So F is going to be QVB. Force is also given. So sine theta must be equals to force upon QVB. So if we just substitute the values here, force is 5 newtons. It must be divided by the charge, which is 0.25. Must be divided by 0.5 as well as the field, or you can say the speed. Divide it by 2 into the power 0.2 we are getting. So 1 by 5. So theta is going to be sine inverse 1 over 5. So you can leave it till here as well. It is not mandatory to find it uh, in points or in any other terms. So I would suggest you to solve at least 10 to 15 problems on this particular topic. Chapter is completely done.